This question is about nitrobenzenes. Nitrobenzene, so remember that's a benzene ring, not very well drawn there, but we're squeezing it in, is reacted with a mixture of conc nitric and conc sulfuric. Then you can get 3 isomeric dinitros. So it could be that it goes 1, 2. It could be that it goes 1, 3. So we're getting 2 nitro groups. Or it could be that it goes 1, 4. 3 isomeric dinitros. Write an equation for how concentrated nitric and concentrated sulfuric react to form the species that reacts with nitrobenzene. So the electrophile, if you think about putting your hand over everything on the benzene ring except what you're adding, and you're adding an NO2 via the N, so there's an NO2 with a plus on the N, it forms that because the sulfuric acid donates a proton, and we also form water. You may have learnt an equation with 2's in front of that gives you protonated water. That's also fine, but this is the simplest version. So this is a benzene mechanism, so we know it's electrophilic substitution, but when we look at the mechanism we can explain why if we look at what we draw. So we're starting off with nitrobenzene. It does want us to form the 1,3, so we're going to pay attention to that in the middle step because that's important in the middle step. What I like to say to students to help this work out well is I want to attach this NO2 group, so I'm going to put the plus on the N. I want to attach it to position 3, so I'm going to go from my pi bond, I'm going to take the electrons from my pi bond, I'm going to go out of position 3, that's where I want it to go. This is where it's important that it said 3. So I've put the NO2 group on 3, the H is still there. So it was electrophilic because a pi bond donated the pair of electrons to an electrophile. Okay, so it was an electron pair acceptor. It's substitution because we're going to swap the NO2 for a H. Now in this intermediate, the mark is for your pi bond needs to extend from the 2 carbons either side of the additional group. It doesn't help that my ring's not very symmetrical here, but can you see how I lined up with the 2 carbons either side of the addition and I drew a horseshoe. I'm going to put the plus inside that horseshoe and then I'm going to use the pair of electrons on the bond to the H to put them back into the ring to reform our pi bond and give us back that delocalized stability. I can draw that with the NO2 on position 3 and a hydrogen. So we've swapped an NO2 for a H and we've done it using an electrophile. So the dinitrobenzenes shown, so we've got the 1,2 and the 1,4 were investigated by TLC in an experiment carried out in a fume cupboard. So this is required practical 12. A concentrated solution of pure 1,4 dinitrobenzene was spotted on a TLC plate coated with a solid that contains polar bonds. So the stationary phase is polar. And then it says hexane was the solvent. So the mobile phase, hexane is a non-polar hydrocarbon, was non-polar. So non-polar things are going to move, polar things are going to stay. Mobile moving phase, non-polar. Non-polar moves, stationary phase polar, polar stay. The start line drawn in pencil, the final position of the spot and the final solvent front are shown on the chromatogram. And we've got to deduce the RF value. Now I'm going to have to do this on this electronic screen, so my ruler values are probably not going to be the same as the ones that you have in your pack on your piece of A4 paper, or if you've got a smaller version, it's not going to be the same as your smaller version. But what you want to do is measure the distance from the start line to the solvent front, so using your ruler, from the start line here to the solvent front, doesn't want to stay here. You're going to measure that in whatever units you like, as long as you stick to the same units. So on my ruler, that's 8.4. Now, then you want to measure from the start line to the spot. So I'm just going to move my ruler over slightly. And on that, it's 5.2. Now, that doesn't mean those will be your numbers. You will have to use a ruler on your piece of paper. It depends how big you've scanned or got this question. That's coming out to be 0.62 to 2 decimal places. So then I would pick the answer closest to that, which is D. So I'll put a tick in the box. That is correct. If you had just done it by eye, you could probably have guessed it was D, because it looks like it's more than halfway up the paper. So it was going to be C or D, and then use your ruler to work it out. The next thing says, state in general terms, so this is just really state a statement that's out of the specification, what determines the distance travelled, and it's determined by the balance between solubility in the moving phase or mobile phase, if you want to call it that, and retention. So it's a balance between solubility in the moving, how much it dissolves, so how much it likes the moving phase, compared to how much it's retained by the stationary phase. So if I change the stationary phase from silica to a piece of paper, so if you've ever compared a TLC plate to paper chromatography, you'll get different RF values because the stationary phase has changed. Even if you use the same solvent, it doesn't mean you'll get different answers, because your data book values would be different as well. But it's the balance between solubility in the moving phase and retention by the stationary phase. And then it says, to obtain the chromatogram, the TLC plate was held by the edges and placed in the solvent in a beaker in the fume cupboard. The lid was then placed on. Give one other practical requirement when placing the plate in the beaker. So this is just a little test of whether you remember from when you did this, that when you put that plate in there and you've got that pencil line drawn on it, that the solvent must not go above the pencil line. Otherwise, all your sample will just dissolve into the solvent rather than be carried by it. And it says a second TLC experiment was carried out using 1,2 and 1,4 with an identical plate. So this one we had here, which was mobile phase non-polar, stationary phase polar. So the same solvent, same plate. 1,4 was found to have a greater RF. So 1,4 moves more. So we go back and we see which our moving phase was, and our moving phase was non-polar. Okay, so 1,4 moves more. Okay, so because 1,4 moves more and our moving phase was non-polar, so it must be more soluble in non-polar moving phase, then 1,4 is the more non-polar one, and we're being asked to deduce the relative polarities. So 1,2 is more polar than 1,4. 1,4 was more soluble, so must be more non-polar. Okay, the question continues. A third TLC experiment was carried out using 1,2. An identical plate, so remember this was our polar plate, was used under the same conditions, but the solvent now suddenly has both these two chemicals in when this one is polar, so the solvent is suddenly more polar. A student stated that the RF value of 1,2 in this third experiment would be greater than 1,2 in the experiment 2.6. So remember that 1,2 was our more polar nitrobenzene, and our moving phase is more polar now. So the student is correct. Yes, they are correct. Okay, the solvent is now polar, okay, because ethyl ethanoate is polar. So the polar isomer will move more, as is, remember it's that balance between solubility and retention, as is more soluble in the moving phase than it was before. So it's going to move more because it's more soluble in the moving phase.